Hello, I'm Keith Van Grafflin with Esri. I've been working with Emily Smale and Danny Jafari on this project that I'd like to discuss with you. So SDGs are monumentally important, and we want to share a project that we're working on to make SDG data more actionable within using a GIS. So it makes me think of a quote from Ban Ki-moon, who was the 8th Secretary General of the United Nations. Saving our planet, lifting people out of poverty, advancing economic growth, these are one and the same fight. We must connect the dots between climate change, water scarcity, energy shortages, global health, food security, and women's empowerment. Solutions to one problem must be solutions for all. So this work that we've been doing comes out of a mandate that came from the UN Environment Program. It really urges organizations to provide methodologies to use and harmonize country data for coming up with comparisons to address sustainable development goals. And that's what we've been doing with this project specifically. So over the past year, we've been working with GEO, specifically the GEO Blue Planet team, the UN Environment Program, NOAA, and Plymouth Marine Laboratory on SDG14, Light Below Water. And specifically, we've been working to develop an index of coastal eutrophication. So what's important here is understanding what eutrophication is, and these are impacts that are caused by anthropogenic or human activities on land, mainly in the agricultural and industrial industries. So this is when extra nutrients make their way into the environment, usually during a rain event, and they're transported through our rivers, our streams, and our stormwater outflows that eventually drain to the ocean. And that's why monitoring for this SDG is so important. As people, we can make changes and do something about it, and understanding when these events are happening is the first step to do that. Using satellite observed chlorophyll, we're able to understand the concentrations of chlorophyll values throughout our oceans and waters. There's a concentration level that can be associated with nutrient-rich waters, and those areas with higher concentrations are easily identifiable and detected with satellite measurements. So for this project, we had a couple goals. The first one is to quantify the number and severity of eutrophication events in the nearshore waters globally. That's within the exclusive economic zone for each one of these countries. The methodology is using those satellite measurements in order to detect that over time. So Esri supported implementation of this methodology within a GIS framework, and that did not happen overnight. So we had several iterations working with the group of experts in Ocean Color to take their methodologies, apply it, and go back and refine the methodology based upon the results that we were presenting. The final methodology was adopted in by the UN in the most recent update of the Global Manual of Ocean Statistics. And this methodology is scalable, so it scales to any region, and it can be applied at many different scales of geography and data. So there's a huge opportunity here to take this workflow that we've implemented on level 1 and apply it to your own country or regional level data within level 2 or level 3. So this within ArcGIS Pro, we are able to create a repeatable and understandable workflow that can be easily tuned or modified. So there's parameters that you can go in and tweak, and this was done through a series of model builder models. For sub-indicator 1, the question we were trying to answer was, what are the annual trends for a country? We used the Plymouth Marine Laboratory Chlorophyll A product for this. This is a product that was developed for the Ocean Color Climate Change Initiative. And for this annual reporting, we're looking at monthly means between the years of 2005 and 2019 and comparing that to the baseline values that we computed from this same PML product for years 2000 to 2004. So a 5-year baseline was used, and we compared the years of 2005 to 2019 against that baseline, and in order to come up with a deviation number. And that deviation is a percentage for each of the countries' EEZ that was impacted by counting the number of pixels that were above the 90th percentile. Here's a look at the workflow for sub-indicator 1. So we would take the monthly value, chlorophyll value, we would take the baseline and we would subtract that. We would take that result and divide it by the baseline, and then multiply it by 100 in order to come up with a percentage. At which point we would select only the positive values and clip that entire image to the global exclusive economic zone boundary. That was agnostic of any country, just the global EEZ boundary. At that point, we would look at all the pixel values and determine which ones were, what the 90th percentile cutoff value is, and then we would classify those pixels that are above that 90th percentile as a deviation. We would then summarize it by each country's exclusive economic zone and produce a monthly summary table. So here's just a quick look at what that the results of the sub-indicator 1 chlorophyll A monthly deviation is. So here you can see in the light gray areas that are the outline that surrounds the country is the country's exclusive economic zone. The values in the yellowish color are your actual deviations, and this is a time series that's going from 2005 to 2019. Here you can see the temporal trends in the data. So eutrophication is often associated with warmer water temperatures. So in the summer months in the northern hemisphere, we see an abundance of the 90th percentiles located at the northern latitudes, and as summer occurs in the southern hemisphere, we see those pixels migrate southward into the southern hemisphere and occupy that space due to the warmer temperatures. For sub-indicator 2, we're trying to answer the question, how often are these blooms occurring? In order to address this question, we use the NOAA Chlorophyll A product that comes off of the VIIRS platform. So we're looking at daily anomalies between 2018 and present and calculating a monthly frequency to describe that. So in this case, we had 3 different levels that we were classifying to based upon the severity of the anomaly. That would be the 90th, 95th, and 99th, and that would be moderate, high, and extreme respectively. And again, for this one, we're looking at a frequency. So every day there's not a valid collect due to the nature of satellite observations. So we would see how many valid collects were within a pixel, and then compare these moderate, high, and extreme levels to that number of valid collects and derive a frequency. Here's a look at what that workflow is. In this case, we're taking the proportional difference product that comes from NOAA, that's already an anomaly that's been calculated, and we're clipping that to the global EEZ boundary. And at this point in time, we are doing statistics to derive that threshold cutoffs for the 90th, 95th, and 99th percentiles respectively. We're also doing a pixel count to understand the number of pixels that were occupied by data within a month. We would classify each one of the percentiles to extreme, high, and moderate, and that's what we see happening here in step 1. Within step 2, we would do a division of the number of pixels that had actual data in it per day. So we would sum those up and have an understanding of how many valid collects were occurring within the entire month, and use that to derive the frequency for each one of the cutoff values. In step 3, we are summarizing that by each country by clipping those pixel values to a country's exclusive economic zone. And then in step 4, we are summing up, each of the 12 months into an annual product to understand the amount of extreme, high, and moderate occurrences within the entire calendar year. So here we go. Let's take a look at how we compute a daily anomaly for subindicator 2. So in this case, we're taking the 99th day of the year, which is April 8th, and we're going to look at the values of chlorophyll A, proportional difference within that image. So in this case, we get a histogram, and what the histogram shows us is everything that's in gray is below the 90th percentile. The values that are in yellow make up our 90th to 95th percentile. The values that are in the purple or pink color are the 95th to the 99th percentile, or our high classification. And then our values in red are our extreme classification, and they make up the 99th percentile or greater, and they're found within the right-hand side of this histogram. And what this looks like, once we have the chance to put it on a map, we can look at the subindicator 2 daily anomalies. And this time series goes from January of 2018 until the last day of September of 2020. And you can see that there are pixels that are occurring classified to the moderate, high, and extreme levels within each country's EEZ. And the EEZs are shown in the boundaries around each one of the countries that are in light gray. So here we can see the chlorophyll concentration image on the left-hand side. That comes from the VIIRS platform. And then on the right side, we can see the algal bloom index for this particular day. So this is April 8th, the same day we were looking at, and what these values look like once they are classified to the associated percentiles. And here we can see for subindicator 2 the different levels that the different frequencies that are being calculated and how they're being computed. So here we would take the number of monthly moderate occurrences divided by the total monthly occurrence within that pixel, and then we would summarize that by each country's EEZ by providing a count and a mean. We would do that for moderate, high, and extreme levels. So again, this is a methodology that is scalable, so it can be scaled up and looked at used to look at level 2 and level 3. This workflow, it can be used at any geographic scale and with regional level data. And so there's an opportunity here for countries, individual countries, to get involved and apply this methodology at a more localized scale. The next steps for us are taking this information and making it available through the ArcGIS Living Atlas of the World. So we'll be hosting the results for Subindicator 1 as well as Subindicator 2. And we're developing a web application to review those results and provide the supporting data to the UN reporting. This will enable users to understand the coastal eutrophication on a pixel by pixel basis within their respective countries. So if I wanted to know more and the reporting numbers, I could see what was going on and an upward trend in my country. I could go and use this application to look at specific areas where those trends were occurring and maybe set up some sort of a network for water quality monitoring and start to identify point source pollution locations. So lots of opportunities from coming out of the web application to increase understanding and to get involved and make this data actionable. So my name is Keith Van Graafland. I encourage you to reach out to me. I support ocean content at Esri and making that available to our community. I'm a product engineer on the Living Atlas of the World team, and you can get in contact with me with my email address here. Please reach out with any questions you might have. And thanks for the opportunity to share this project with you today.